This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, we were developing the mathematics of linear operators. As I've emphasized, the mathematics of quantum mechanics is linear algebra. Linear algebra consists of a set of concepts beginning with a vector space. The vectors represent the states of a system in ways that will become clear. If that doesn't ring a bell and doesn't make sense to you now, that's okay, just as long as you understand the mathematical rules of vector spaces at this point. The states of a system are, of course, not what you measure. What you measure is observable quantities, things like momentum, things like other quantities that are available to detect and to record and to measure. And the measurable quantities are represented not by vectors in the vector space, but by linear operators, Hermitian linear operators. So we need to develop that concept. We started, I don't know how many times we've started, but let's just review very, very quickly. A linear operator, I won't explain to you again what linear means, but a linear operator, let me find a piece of chalk. This is not chalk. Yeah. A linear operator I will represent by a capitalized letter, and I'm going to put a little hat over it just to indicate that it's a linear operator. It acts, it operates, it does something to vectors. In particular, it does something to ket vectors and gives you new ket vectors. I'm going to call this one C. All right. Now, that allows us, that together with the idea of the dual vector space and the notion of inner product, allows us to define what are called matrix elements of operators. Matrix elements of operators kind of are numbers. They're all numbers. They're a collection of numbers, a number for each pair of states that you can write down, each pair of states, let's say A and B. All right, and they're simply defined, let the operator act on A. It gives you a state. It gives you another vector. Let me put a bracket around it to indicate that K has acted on A to give a new state that I could call C, but let me just leave it this way. And now take the inner product of that with another vector B. That is usually simplified, the notation for it is usually simplified just to B, K, A. But the way that you read it is K acts on A to give a new vector, K times A, and then you take the inner product with B, and the result is called the matrix element of K. I should put some hats over this, shouldn't I, to indicate that it's an operator. This is sometimes just more briefly called KBA. It's called the matrix element of K between vector B and vector A. And it's a notation that's very closely related to matrix notation. Now, remember the idea of a basis of vectors. A basis of vectors is a collection of vectors which I can label N. If the dimensionality of the vector space is whatever it is, D for dimension, then a basis has D independent vectors, all of them orthogonal to each other and all of them of unit length. So just pictorially, a basis, it's hard to draw vectors in a complex vector space. The best I can do is to draw them in a real vector space. But for example, these would be a basis of vectors in ordinary real three-dimensional space. There are other bases. Another basis, for example, would be, let's see if we have another color of chalk. Another basis might be tilted relative to this basis. These are intended to be all mutually orthogonal vectors, all of unit length, the blue vectors, in 3 dimensions. And these are two different bases, the blue basis and the black bases. Let's pick a basis of vectors. So let's erase the blue basis and simply enumerate the basis vectors 1, 2, and 3, for example. And that's the collection of ket vectors n. Can we represent red states in blue? Boy, Michael, you're on tonight. We could be all home listening to the president give the last State of the Union address. Has everybody decided who they're going to vote for in the primaries? You haven't. I better know which party you're going to vote for. Anybody who would vote for the other party, out of here now. Okay. Yeah. So given a basis of vectors, we can tabulate or record all of the matrix elements of K between vectors n and m. And that's a table. It's a kind of table, a square table of elements, n by n matrix. An n by n matrix, K11, K12, and so forth. Let's put K21 down here. And we tabulate them, write them all down. It makes a matrix. An a square matrix whose size is equal to the dimension of the space. Okay? So those are the matrix elements of K. And they really do describe the entire operator K. They describe it in some detail. They uniquely describe it, yes.
So you mean M to be another base?
I mean n and m to be basis vectors drawn from the same basis.
Oh.
Right. N and m are basis vectors drawn from the same basis. All right? So this could be n equals 3, m equals 2, and so forth. So since there are how many basis vectors? There are d, where d is the dimension of the space, d basis vectors, and therefore d squared matrix elements. N can run from 1 to d, m can run from 1 to d. Okay, now let me remind you about something else. I'll write it over here about a basis. A basis has the property that you can expand any vector in it. That you can take any vector, whatever, let's call it A, and write it as a sum over n of a set of coefficients, let's call them A sub n, times the basis vector n. We sum over the basis vectors. I'll include the summation signs so that any vector can be represented in terms of them. That's just a statement, the analog of the statement that in 3 dimensions any vector can be represented in terms of 3 basis vectors. Okay. Again, the set of coefficients A sub n is nothing but the inner products of the nth basis vector with A. Is equal to A, let me call it M. Let me call, this is supposed to be an M. So the particular coefficient A is just given by the inner product of A with M. That allows us to rewrite any vector in the interesting form sum over n. Now, let me write down the vector n first. Write n first, and then after having written n, let me plug in the coefficient na. This is a kind of expression that will occur over and over where you see an n standing next to an n like that, summed over. Whenever you see that, it's just a way of, oops, this should be closed like that. A is a vector. Whenever you see an expression like n standing next to n with their noses pointed toward each other, summed over n, you can always say all of this sort of does nothing. It just gives you back A. So keep that in mind. Whenever you see a sum like this with n, you can, it's there, it's a real thing, but it sort of just can be thought of as, what is it? It can be thought of as the unit operator. The unit operator on A gives you back A. But if you didn't understand that, it's not important. This is a correct expression. So now, let's go back to the action of the linear operator k on an arbitrary vector. Let's take k and apply it to A. Okay. What I want to do is I want to calculate, let's come back over here. One way of describing the vectors is just to describe them symbolically or abstractly as vectors, but another way is just to give the coefficients A sub m. If I know all the coefficients A sub m, I know the vector A. In particular, if I have a specific basis picked out, the set of coefficients is a representation of the vector. It's a way of describing the vector. And so there's an abstract notation for vectors, and there's a more concrete way of describing them as a collection of components. These are the components of the vector. Now, here is an abstract operator being applied to an abstract vector. I'm interested in working this out in terms of the components of the vector, the actual numerical components of the vector. So the first thing I might like to know, k times A is a vector. I would like to know its components. Its components are just gotten by taking the inner product with the basis vectors. So this is the nth component of the vector k times A, or k acting on A. Let's work this out by writing A in terms of components. Here's A written in terms of components, or like this. So let's plug in for A M, M, A, summed over M. That's the same expression that's written here. The only difference is here I've used the index n for the summation variable. Here I've used the index m for the summation variable. And now we can rewrite this as k n m. This is the matrix element of k between the basis vector m and the basis vector n times A sub m summed over m. So we can reduce the problem of calculating the components of k times A to a set of operations all on components and matrix elements. This is another way of writing the matrix K acting on the column vector A. All right. I assume that everybody here has done a little bit of homework and learned a little bit of linear algebra. This is simply another way of writing the matrix K times the column vector A to get another column vector. This is a column vector because it's a vector whose components are labeled by n. So here's an example of the application of matrix notation or matrix construction to the idea of a linear operator acting on a vector. Now, we can multiply linear operators together. What does it mean to multiply two linear operators? Multiplying two linear operators, let's call one of them, what have I called it? L. Let's k times L. K times L, if k and L are operators, is another operator, which means that it can operate on a vector A. All it means is you first act with L on A to get a new vector L times A. Let's say we can write it this way. It's k acting or operating on the vector L multiplied by A. So L times A gives you a new vector, and then you hit the whole thing with K. So whatever L on A does, then hit it with K. That defines the operation K times L. But now there's an interesting question we can ask. If operators are characterized by matrix elements, what are the matrix elements of a product like K times L? Incidentally, as most of you probably know, K times L is not necessarily the same thing as L times K. These are operators, they're not numbers. One has to check whether you can change the order of them, and in general you can't. Linear operators are not commutative. You can't change the order necessarily in which they act. All right, so let's consider the matrix elements of K times L. What does that mean? That means, that means sandwich the operator K times L between the basis vectors n and m. All right, now, here is L times m. Let's write that in another way. Let's write that by writing L times m is the sum over yet another index. I need a summation index now, so let's call that summation index r. Right. We take L times m, we take its inner product with r, and then we multiply it by the vector r. Again, this construction where you see r's and r's nose to nose like that, it simply means, it simply gives you back the left-hand side. Oops, there's a missing bar in here. There's a missing vertical line in there. Okay, so that's L times m. Let's plug it into here. And then we can write that this is equal to n, K with a little hat on top of it. And then let's substitute this in for L times m. It's r, summed over r. Okay, now we have a nice construction. We have everything written in terms of components. Let's get rid of this. And we can now write that the components, or the matrix elements, let's call it K times L, the n-mth matrix element of it. This is the n-mth matrix element of K times L. What is that given by? It's given by nkr, that's knr, times LRM summed over R. All right, again, this is simply matrix multiplication written out in longhand. The matrix representing KL is simply the product of the matrices of K and L. That's what this reads. This is longhand notation for the matrix product of the matrix K and L. So multiplying linear operators is an abstract idea. You simply follow the action of one operator by another operator, or it's a concrete idea that you can represent by matrix multiplication. Now, I'm not going to go very heavily into this because I'm going to assume that everybody knows it. Among other things, it was discussed elaborately in the last class on quantum mechanics, which I gave on quantum information and entanglement. So I will assume everybody knows how to relate this to matrix multiplication. Next idea, the idea of a Hermitian operator. Hermitian operators are special classes of operators. They play the role in operator theory of things which are real. Real in the sense of real versus imaginary, or real versus complex. Let's let's define Hermitian operators. First of all, let's spell Hermitian operators. That's not right. What's that?
Some people like the E there.
Where?
I mean, Hermite.
Hermite.
Yeah, Hermitian.
Yeah, Hermite. Hermite is not a bug. It's the name of a mathematician. And Hermitian, Hermite is a proper noun. Hermitian is an adjective. Hermitian operators. What is a Hermitian operator? Well, it stands for something which in classical mechanics would be a real quantity, a real thing that you can measure, such as location of a particle, the x-coordinate of a particle, the momentum of a particle, the angular momentum. All of those are real quantities, real as opposed to imaginary. All right, so a Hermitian operator, and I'm going to call a Hermitian operator by the generic term H. Now, later on, H is going to stand for Hamiltonian. For now, it just stands for Hermitian. So let's not worry about Hamiltonians yet. It just stands for Hermitian. Hermitian operators, as all operators, have little hats on top of them. Hermitian operators are defined in the following way. Their matrix elements are such that if you interchange the bra vector and the ket vector, keep the operator the same, then all that happens is it becomes complex conjugated. If you think about it for a moment, if complex conjugating A, the complex conjugating the ket vector A gives the bra vector A, and complex conjugating B gives you the bra vector B, then in order to get a complex conjugate of the left-hand side on the right-hand side, you should also have to complex conjugate H somehow. But H, the Hermitian operators, are exactly the ones that you don't have to do anything to in order to get this to work out. Let me give you another example. Supposing we sandwich a Hermitian operator not between two different vectors, but between the same vector. In other words, take A, H, A, where A could be any vector whatever. Well, according to this equation, it's equal to A, H, A, complex conjugate. Interchanging the bra vector and the ket vector will do nothing if the bra vector and the ket vector are the same, but then this equation just says that the left-hand side is the same as the complex conjugate of the right-hand side. And things which are their own complex conjugates are real. All right? So sandwiching a Hermitian operator between the same state on either side necessarily gives you something real. Incidentally, this can be taken to be the full definition of a Hermitian operator. All right? You can derive the top from the bottom. You can derive the top from the bottom. I won't bother doing it, but it does follow. So you can take the definition to be any matrix or any operator which, when you sandwich it between the same state or the same vector on both sides, gives you something real. It follows from that that if you interchange the bra and the ket in a matrix element of H, that you get complex conjugate. Another way to write it, H, AB is the complex conjugate of HBA. In particular, it's also true, the same thing is true for basis vectors. So HMN, if M and N stand for basis vectors, is equal to H complex conjugate NM, where I've interchanged N and M. That is those are called Hermitian operators.
What you said there when you asked,
Say it again.
always true that B Hermitian A is real?
Say it again.
B Hermitian, those quantities.
B Hermitian A No,
Okay,
it's a complex conjugate of A Hermitian B.
so it's just A Hermitian A.
A Hermitian A is always real. But the top equation, well, they either obviously, the second equation follows from the first just by setting B equal to A, but it's interesting that the first equation also follows from the second. I will leave it to you to try to prove that. It's a couple of lines of proof, and if nobody can prove it, I'll do it another time. All right, so those are the definitions of Hermitian operators. In order to understand the significance of Hermitian operators, obviously they have a kind of reality property. Reality, again, I emphasize reality in the sense of complex numbers. They have a kind of reality property. But in order to really appreciate the significance of them, we have to go to another concept, the concept of eigenvalues. So let's review very quickly. I'm regarding this as a quick review. The concept of eigenvalues and eigenvectors of operators. Now, in general, when an operator acts on a vector, here's a vector, an operator acts on it, it will do something to that vector. One kind of operator might rotate the vector, another might reflect it about some axis. There are all kinds of linear operators, but in general, it will change the direction of the operator. It will take you from here, for example, to here. There may be special directions, particular directions, which, when you apply the operator, for each operator, given an operator, there may be specific directions, and there will be for Hermitian operators. If you have a Hermitian operator, there will be directions that if you apply H to vectors in those directions, it doesn't change their direction. Okay? For example, a simple operator that you can think about would be an operator which takes every vector in any direction and stretches it along an axis. Stretches it out along one axis, doubling its length in one direction, keeping its length in the other direction fixed. So we might have an operator which takes any vector and doubles the x component of the vector, for example, leaving the y component fixed. Then if I take an arbitrary vector, its direction will change, exactly as you see here. But if I take a vector along the x-axis, then its direction doesn't change. Right? The direction stays the same. Those vectors whose direction do not change when you apply a certain operator are called the eigenvectors of that operator. Eigen is the German word for proper. I think proper. Is that what eigen means? Doesn't change? I was once told it meant proper. Yeah, very, very little, literal. Own, okay, good. All right, so the eigenvectors of an operator are the vectors whose direction don't change, but what does happen to them then? Let's suppose we have a operator. I'm taking it to be a Hermitian operator now, and I find some eigenvector. Let me call the eigenvector lambda. What can happen to it? If its direction doesn't change, the only thing that can happen to it is it gets multiplied by a number. Let's call that number lambda. Now, the first lambda here is just a notation for indicating a particular vector. If we find a vector that when h applies to it, when h attacks it, just multiplies it by the number lambda, we call that vector the eigenvector of h with eigenvalue lambda. Eigenvectors, I'll call them E vectors and E values. The eigenvector lambda corresponds to the eigenvector lambda if h hitting that eigenvector simply multiplies it by the number lambda. That's the, yes?
That means then I'm trying to follow this through.
Well,
It doesn't seem like all operations would have eigenvectors.
Say it again.
It doesn't seem like all operations would have eigenvectors.
All operators. Yeah. All linear operators. Yes. That is true. Not all operators have eigenvectors. All Hermitian operators do. All Hermitian operators, and we're going to state a theorem now. Now, I'm not going to prove the theorem. The theorem can be found on the internet version of my last quantum mechanics class on entanglement and that sort of thing. The theorem is an elementary theorem. It has various pieces. Theorem number 1. All of the eigenvalues of a Hermitian operator are what? Real. Okay? These are all easy to prove statements, very easy from the definition. Right? Basically, this alone, that the matrix element of a Hermitian operator sandwiched between the same state is always real. That's sufficient to prove it. I'll let you figure it out. So number 1, E values of Hermitian operators H are real. Real numbers. Okay. Second part of the theorem, or second theorem, 2. Very easy to prove, as I said. The eigenvectors of Hermitian operators for different eigenvalues. If I find more than one eigenvalue, if there is more than one eigenvalue, let's call it lambda 1 and lambda 2, and they're not equal to each other, different eigenvalues, the eigenvectors are what? Orthogonal. For lambda 1 not equal to lambda 2. In other words, for 2 different eigenvalues, the eigenvectors are orthogonal. This is not true of general operators. It's true of the Hermitian operators. Number 3. Basically, number 3 says there are a lot of eigenvectors of Hermitian operators. How many is the maximum there can be? Well, they're all mutually perpendicular, for different eigenvalues, they're all mutually perpendicular to each other. How many mutually perpendicular vectors can you find in a d-dimensional vector space? Well, maximum is d. The theorem says that there are always there exist d mutually orthogonal for Hermitians, not only at most, but also at least. Hermitian matrices have d mutually orthogonal eigenvectors. If 2 of the eigenvalues for 2 different eigenvectors happen to be the same number, still you can find orthogonal eigenvectors associated with them. In that case, the 2 eigenvalues, if they happen to be the same number, are called degenerate. But let's ignore the possibility of degenerate eigenvalues for the moment. What does this mean? This means that the eigenvectors of Hermitian operators form bases. In other words, there's enough of them, they're all perpendicular to each other. You can always choose them to be unit vectors. Why is it that you can always choose them to be unit vectors? How do I know that I can always take an eigenvector to be of unit length, unit norm, unit inner product with itself? Well, if I have an eigenvector and I multiply it by any number, it's still an eigenvector with the same eigenvalue. In other words, if I take twice lambda here, that 2 just goes straight through. H on twice lambda is lambda times twice lambda. So if I multiply an eigenvector by any number, any just ordinary complex number, it could be complex, any complex number, it still stays an eigenvector with the same eigenvalue. So I can always multiply the eigenvectors by numerical numbers until I get them to be of unit length. Once I have them of unit length, and they're all mutually orthogonal, they form a basis. This is the basic fact, two basic facts about Hermitian operators. Their eigenvectors form a basis, and their eigenvalues are all real. Any questions up till now? Okay. Yes.
So confused about whether they exist or not. So,
Whether they exist.
so the rotating the axis isn't Hermitian?
Say it again?
Rotating?
No. Rotating axis is not Hermitian. Right. Actually, I'll tell you, it's anti-Hermitian. We'll come to the definition of that in a minute, which means if you multiply it by I, it becomes Hermitian. Now, you can ask, well, if you multiply it by I and it becomes Hermitian, that must mean it has a bunch of imaginary eigenvalues. Yes, rotation operators do have imaginary eigenvalues. Remember, we're dealing with vector spaces over the complex numbers. Just an ordinary rotation happens to have a complex eigenvalue. But if I were thinking about real vector spaces, in real vector spaces, rotation of axes does not have, is not Hermitian. So that's exactly right. What does Hermitian become? What's the concept of Hermitian? Do we have it here? Yeah. What's supposing we're talking about a real vector space where all the numbers, matrix elements, everything else are real numbers. What is the analog of Hermitian? The analog of Hermitian, we just ignore complex conjugation. No such operation is complex, or everything is its own complex conjugate, and it's symmetric. HAB is equal to HBA, or HMN is equal to HNM. So a special case of Hermitian operators would be symmetric real, things which are symmetric and real. Okay? A rotation of coordinates is antisymmetric, is an antisymmetric matrix. So in that sense, it is not Hermitian. So you.
You said that the eigenvectors form
A basis.
a basis of the, in which, is there a relationship? In what space? I mean, is it even?
The vector space, the complex vector space.
Is there a relationship between that and H and some, H and some kind?
Given an H.
There would be more than one dimensional vector space. Can there?
Yes, but let's focus on a particular vector space. And now take a certain particular Hermitian operator in that vector space. Okay? It's a collection of vectors. Hermitian operators act on that vector space, give new vectors, take that. Now, if you want a concrete representation of it, then the concrete representation is in terms of matrices. Basically, this says that every Hermitian matrix has a complete orthonormal family of eigenvectors.
Well, plus the form of H in that basis is very simple.
And it's also simple. Well,
It's just got the eigenvalues on the diagonal.
yeah. In that basis, yes. In that basis, the form of H is very simple, but it may be a difficult job to figure out what that basis is. So I didn't want to belabor that point right now, but you're right. All right, so if you like thinking concretely, really concretely, and not abstractly, as I do, then it's easy to think of operators simply as matrices. Matrices, H11, H12, blah, 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 H21, dot, dot, dot. Vectors as column vectors, A1, A2, A3. And then acting with a matrix on a column vector, I will assume you know how to do that, gives you a new vector. If A is an eigenvector, that means that the matrix, when it acts on A, just gives you a number lambda times the same vector, if it is an eigenvector. Not all vectors will be eigenvectors. Most won't. Most vectors won't be eigenvectors, but there will be a complete basis of them if H is Hermitian. So if you like thinking concretely, just think in terms of matrix elements. Now we're ready to state the postulates of quantum mechanics. The first postulate we've already stated. The first postulate is that the states of a system, the configurations, the conditions describing a system at a given instant of time are described by vectors in the vector space. So, states equal the collection of Ket vectors. You could use the bra vectors. They're in one-to-one correspondence, but let's focus on the Ket vectors. That's the first postulate. For every state of a quantum mechanical system, there exists a vector in a vector space. How many dimensions does the vector space have? That depends on the particular system. If the system is a coin, and that's all, and it can be heads or tails, then it's a two-dimensional vector space. There are only two orthogonal states, two mutually orthogonal states. If it's a die with 6 independent states, then the dimensionality of the space is 6. Real systems typically have a lot more states than that. And for example, a particle moving in space could be located, if we looked for it, at any position. So it would have an infinite number of states. But for each state, there is a Ket vector. So that can be taken to be postulate number 1. Now, the number of postulates I'm going to write down is a little bit more than is absolutely needed to minimally axiomatize quantum mechanics, but it's nice to write them all down in a way which exposes the ideas and not try to be absolutely minimal. Okay. Yes? Say it again. You don't observe the states of systems. You observe the observables. The observables correspond to the Hermitian operators, but we'll come to that. Nobody has ever directly observed the state of a system. You observe the things which can be observed, which are things like position, momentum, electric field, magnetic field, things which record measurements on an apparatus. And they never, never, never give you enough information to be able to record the whole state of a system. So you would never call a state of a system an observable. Okay. We'll talk about later, at some point, we'll talk about how you prepare states. I don't know if we will. That was talked about a previous quarter. For the moment, states of systems are described by vectors. That's postulate number 1. Postulate number 2 is the things which you observe. Now, observe means you make measurements of them. You could call them observables, you could call them measurables, you could call them the things that you measure in an experiment. The things that you measure in an experiment, we'll call them observables. That's the usual term for them. The observables correspond, we should really write this not equals, but corresponds to the collection of Hermitian operators. The collection of Hermitian operators. Every Hermitian operator corresponds to something that you can measure, in principle. Not any old operators, but the collection of Hermitian operators. Number 3, third postulate, the values. You're going to do an experiment now, and you're going to observe a particular observable that corresponds to a Hermitian operator H. What are the possible results that you can get of the measurement? You make a measurement of H, whatever H is, and you get a value. The possible values that you can get, the collection of values that you could get, the values of the observable H are the eigenvalues of H. That's the meaning and the significance for us of eigenvalues. They're the values of the quantity that you can get when you measure it. So they have, in other words, they're important is the point. Not only are they important, as I said, they are the things which you get in an experiment. What else? Oh, and remember, anytime you do an experiment of a quantity, you get a number, and it's always a real number. If I measure the position of something, I don't get a complex number. I get a real number. If I measure the x-coordinate, or if I measure the angular momentum, or if I measure, whatever, electric field, I get a real number. So it's important.
Error bars. With error bars.
No, they usually, if you measure the angular momentum, there's no error bar in the imaginary direction. You may have error bars in the real directions. It's a real number. Okay, therefore, it's important that Hermitian operators have real eigenvalues. After all, those are the things you can measure. Furthermore, the states for the states which, if you find a system in that state or create a system with a particular state, the states for which the observable h has a definite predictable value, a certain value, a value which is not subject to statistical fluctuations, those states for which the observable h is, let's say, is definite, or certain as opposed to uncertain, are the eigenvectors of h. The eigenvectors of h. In other words, if by one means or another you created an electron in an eigenstate of some observable such as its position, and then you measure the position, the measurement will always yield every time the eigenvalue of the appropriate operator, the position operator. So the eigenvectors are the states in which the observable has a definite value, and the value that it has is the corresponding eigenvalue. Any questions? Yes?
Would it be wrong to say that you could observe eigenvectors?
Say it again?
Would it be wrong to say that you observe eigenvectors?
Well, I think it's more proper to say that you observe the observable and get a number, and the number corresponds to the eigenvalue. I would say that's more proper terminology and a more proper way to think. Of course, once you do that, then you know that the system was prepared in a particular state, and in that sense you could say you observe it. But I think it's a sort of linguistic misuse to say that you observe eigenvectors. It's better to say you observe the observable, and the result that you get is one of the eigenvalues of the observable. And I think that's a more precise language.
So by point 3 and 4,
Say, 4, yes.
3 and 4, what do you mean by H is observable, H is definite?
Okay.
I mean, it's switching from measure-
All right, so let me give you an example. Let's take an example such as the spin of an electron, some particular component of the spin of an electron. If you prepare an electron in an arbitrary state, how do you do that? You put the electron in a magnetic field. Go back to Course on Quantum Mechanics number 1 and read about how you prepare an electron with its spin along a particular axis. Supposing you did that, and then you measure the spin along some other axis, then you may get plus or minus. You may get, with a certain statistical probability, you will get different answers. But if you measure the spin along the axis that you prepared it along, then you will get a definite answer. You'll get a definite answer corresponding to the spin the way that you prepared it. So there are certain states which, if you measure certain quantities, you will always get the same answer. You do a certain experiment on this. An experiment, I mean, you place it in a field, you do something to it, and at the end of doing something to it, you measure something. Sometimes the measurements will give you statistically ambiguous answers with a probability distribution, depending on what you measure. and depending on what state it's been put in. Other times, if the thing you're measuring corresponds correctly to the state that you've created the system with, then you may get definite answers. We'll see some examples. Definite means there's no statistical uncertainty in the value that you get. Okay? So there are certain states. For each observable, there are certain states where you will definitely get a particular answer, and you'll always get the same answer. Namely, if the system has been prepared in an eigenvector of a particular variable, and you measure that variable, you'll always just get the eigenvalue. All right, so that's the fourth postulate. And the fifth postulate is what happens if you start with a state which is not an eigenvector of the quantity of interest. So in other words, supposing instead of preparing a system with a state which happens to be an eigenvector of h, you prepare some other state somehow. And I'll give you examples. We'll come to it. But let's state the postulates. Number 5. Take an arbitrary state of a system made God knows how, however the system was originally created. An electron may be created by shooting it out of an accelerator or something in some particular way. We make the electron in some particular state, and we now measure something or other about the electron. Okay? We measure the h-ness of the electron. Right? What can we get? We can get answers which are the various eigenvalues. Let's call them lambda 1, lambda n. These are all the possible answers we could get, the various eigenvalues of lambda. For each of these eigenvalues, there is an eigenvector. We can call it, I don't know, let's just call it lambda n. That's the eigenvector that corresponds to a definite value of h with a particular eigenvalue. Then, the fifth postulate is about the probability of getting different answers, lambda 1 through lambda n. The answer is that the postulate is that if you calculate the component of the vector A along the axis lambda n, okay? Think of these lambda n's as a basis set. They're a basis set which goes together with the particular observable, right, made up out of the eigenvectors of that observable. Take the component of the vector A along the direction lambda n. That's a complex number in general. In general, this is a complex number, could not possibly be a probability, but multiply it by its complex conjugate. So multiply this by its complex conjugate. One way of writing it is take the absolute value of it and square it. Another way of writing it is to just multiply it by its complex conjugate, lambda n. Multiply it by its complex conjugate. Its complex conjugate is lambda n times a. You just invert bra and ket, and that gives you the complex conjugate. So take a, no summation here, a projected onto lambda n, squared or complex conjugated, that gives you the probability. That's the probability that you measure lambda n if the system has been prepared in the state A. So whatever went into constructing a particular configuration of an electron, the particular way that it came out of the accelerator, the particular magnetic field, electric field, various conditions under which the electron was created, define the state A. Having created the electron, or whatever the system is, you can then ask, what's the probability that if I measure a particular observable, h, that I get any one of its possible eigenvalues? The answer is the component of A along the eigenvector lambda n times its complex conjugate. This is always a real positive number. Okay? It's always a real positive number. And so it can be a probability. Those are the 5 postulates of quantum mechanics. There are ways of diminishing the number of independent postulates, but I think it's better to expose them all and to say them all, and not try to be clever and reduce the number of independent postulates. Okay, well now I will give you some examples soon enough. I was going to talk about incompatible observables, but let's not at this point. Let's do some examples. Yeah. The simplest examples correspond to systems with finite number of states, like the coin toss or the dice or so forth, but I don't want to begin with that. We've done that, we did that repeatedly in the previous class in quantum mechanics and quantum entanglement and so forth, which is basically about these simple systems with finite numbers of states. Let's jump right now to the motion of a particle on a line. Supposing we have our system consists of a particle in one dimension. The particle can be anywhere on a line. It can move on a line. Classically, we would just describe this by a particle with a coordinate x, which could depend on time. Quantum mechanically, we describe it completely differently, very differently. We describe the states of the particle by a vector space. What vector space? Well, I'll tell you right now what vector space. The space of functions of x. Remember when we started and I gave you some examples of vector spaces, one of the examples of vector spaces was functions of a coordinate, complex functions of a coordinate. Psi of x. Psi of x corresponds to a vector in the vector space of complex functions. We can think of it as a vector in a vector space because we can add functions and we can multiply them by numbers. Okay. We can take inner products of these vectors. Let me remind you of the rule. If I have two functions, phi of x and psi of x, then the inner product between them is just the integral over the line, dx, of phi star of x, psi of x. Why phi star of x? Because phi is the bra vector, psi is the ket vector. So whenever you have a bra vector, it always corresponds to some complex conjugation. That's the definition of the vector space. For a particle on a line, the vector space can be thought of as functions on the axis. Well, actually, it can be a little more abstract than that. We can think of these functions differently. Well, no, let's not be more abstract. We can come back and be more abstract later. All right. Let's think about operators now. Yes?
That integral won't necessarily be real.
Which?
The integral you wrote in
No, inner products are not real in general. What are real is the inner product of a vector with itself. All right? So if I were to put psi, that would be the inner product of psi star with psi. That would be real. Okay? Good. All right. Good question. Keep the questions coming because...
It's implied multiplication of two functions.
What's that?
Implied multiplication of two functions.
Say it again.
Multiply two functions.
Here and here. Yeah, absolutely. Just common garden variety complex multiplication. Right. So that's the inner product. Now, let me give you an example of some operators. We can check that they are really operators. Check that they're Hermitian. Find their eigenvalues. Interpret them as observables. And see what their probabilities correspond to. The first operator is the observable that corresponds to the location of the particle along the axis. Right? And I'm going to tell you what that operator is and how it acts on psi of x. We'll call that operator just x with a hat on it. And it operates on a vector psi. In terms of functions, what it does is it takes a function of x, psi of x, and does something to it. It does the simplest possible thing. It multiplies it by x. That's its definition. The operator x hat acts on the ket vector psi, I should say corresponds to, not equals, in such a way that the new vector, if the old vector was represented by psi of x, the new vector, the result of multiplying it by the operator x hat, is just to multiply the function by x. Very simple. Right? Well, what would it mean to have an eigenvector of the operator x hat? In terms of ordinary functions, it would mean that, or what does it mean, first of all, in terms of the abstract notation? The abstract notation, x hat on psi of x.
If you made the right-hand side a ket, then could you say equal?
Well, no. You can't multiply a ket by x. You can only multiply it by the operator x. Oh, good. Yes, you could do that. Thank you. Yes, that would be legitimate. In other words, it's the ket vector whose representation is x times psi of x and just instead of psi of x. Yes, that's fine. That's good. Okay. Are there eigenvectors? Well, what would that mean? That would mean that x hat on psi of x is just equal to some number. Before that, let's check that it's Hermitian. Let's check that it's Hermitian. What does it mean that it's Hermitian? A necessary and sufficient condition is that A, Hermitian A, is real for all A. That's necessary and sufficient for a Hermitian operator, for any vector A. Okay, let's just check that. All that means is that psi of x, x hat, psi of x is real. But what is that? X times psi of x just corresponds to the vector x psi of x, just corresponds to the function x psi of x. Taking its inner product with the bra vector psi of x means multiplying it by psi star of x and integrating. This is surely real. Psi of x times psi star of x is real. X is real. Dx is real. This is a real number. All right? Whatever psi is, this is always real. So it follows that the matrix element of x between equal vectors is always real. That's necessary and sufficient for x to be a Hermitian operator. So x is Hermitian. That must mean it has a lot of eigenvectors. So let's see if we can find the eigenvectors. The eigenvectors, abstractly, are defined by x hat on psi of x, on psi, is equal to a number times psi. If we can find functions which satisfy that, those are the eigenfunctions, or the eigenvectors of x hat. What does it mean in terms of ordinary functions? All it means, let me erase this, all it means is find a function psi of x so that when you multiply it by x, you get a multiple lambda of the original function. Now that looks a little absurd, doesn't it? A function such that when you multiply it by x just gives you a number times the original function. If you think about it for a minute, that's quite impossible. Well, it is impossible, strictly speaking, but you can get very close to this. So let me show you what's involved. Let's write this as x minus lambda times psi of x equals 0. All I've done is transpose the right-hand side over to the left. X minus the number lambda on psi of x is equal to 0. This should be thought of as an equation for a function psi of x, and it must be true for all x. When you write a thing like this, you mean that it should be true for all x. Well, here's a product of two things which has to be 0 according to the equation. What do I know if a product is equal to 0? I know that at least one of the factors has to be equal to 0.
Did we assume somewhere that the integral of psi star psi converges?
Yes, we will assume that. We will assume that the integral of psi star psi always converges. We'll find out why in a little while. Converges. In particular, that means psi goes to 0 at large distances. Whatever psi is, it should go to 0 far away, do whatever it wants in here, and then go to 0 nearby. The interpretation of that will become clear in a little while. So it doesn't leak off to very, very large distances and get bigger and bigger. It goes to 0. Assumption. Fast enough to make this integral converge. Okay, so let's take x minus lambda psi of x equal to 0. What does this equation tell us? It tells us that anywheres where x is not equal to lambda, here's lambda right over here, x equals lambda right over here, any place where x is not equal to lambda, psi has to be equal to 0. That means the only place where psi is not 0 must be where x is equal to lambda. At x equal to lambda, you can have psi not equal to 0 because at that point x minus lambda is equal to 0. Anywhere else, if this equation is to be true, psi has to be 0. So let's plot what psi has to look like. Psi is a function which is 0 everywheres except at x equals lambda. There's x equals lambda right there. So it's 0 everywheres except at this one point where it can be non-zero. Now, function like this is not a nice, continuous, sensible function. In particular, you can't square it and integrate it, a function which is only non-zero at a single point. And so what Dirac did was to invent a kind of idealized, a generalization of a function. The generalization of the function is probably well known to most of you, and it's called the Dirac delta function. At the moment, I don't want to get deeply into the mathematics. I'm more interested now in illustrating some of the concepts that we've gone through. So let's imagine that what this really means is that it's a function which is non-zero over a tiny, tiny interval. In the end, we'll allow that interval to shrink to 0. Let's call the size of that interval epsilon. Epsilon for small number. Epsilon. And the height of the function we'll take to be 1 over epsilon. That's not in itself very important at the moment. But just to put some area under that function, let's make the function as high as it is narrow. That's a function which is 0 everywheres except in this tiny interval near x equals lambda. Near x equals lambda. It's a high, narrow function which is 0 everywhere else except in that tiny interval. That function is what Dirac called the delta function, delta of x minus lambda. It's 0 except when the argument is equal to 0. Except when x minus lambda is equal to 0, then the delta function is a high, narrow spike. But when x is not equal to 0, or when x minus lambda is not equal to 0, the function is 0. That's called the Dirac delta function. Now, to give a precise mathematical definition, you get uncomfortable with functions which are as loosely defined as this, and you should. There is a precise definition of the delta function. We may or may, yeah.
I thought these supposed to be orthonormal.
That is, yeah. When, yes. It's not orthonormal. It's ortho, but not normal. The reason it's ortho, let's see if it's ortho, first of all. Ortho means, well, first of all, let's prove that this is an well, of course it's an eigenvector of x. It satisfies this equation. X minus lambda times psi of x is 0, either because psi is 0 or because x is equal to lambda. So yes, it is an eigenvector. It's an eigenvector with eigenvalue lambda. But let's first ask about ortho before normal. Ortho means that if I have two different eigenvectors with two different values of lambda, that they must be orthogonal to each other. So let's draw another eigenvector corresponding to x equals lambda prime. That's a function which looks like this. Now, as I said, we will have to imagine in the end that this epsilon shrinks to a smaller and smaller size. But these two functions are orthogonal to each other because when you multiply them together, let's call it phi and psi, when you multiply them together, one or the other is 0 everywhere. When you multiply this by this, one or the other or both are 0 everywhere. Wherever this one is non-zero, this one is 0. Wherever this one is non-zero, this one is 0. So when you multiply them together, you always get 0. And therefore, the inner product of them is certainly 0. On the other hand, if you take the eigenvector and take its inner product with itself, you'll be squaring this high narrow function, and the answer won't be 0. Okay? So they're orthogonal to one another. Normalized, we'll worry about another day. They're not of unit norm. Okay. This is an example of an orthogonal family of functions which are the eigenvectors of the operator x, one eigenvector for each value of lambda, for each possible position along the x-axis. Now, in fact, we've even found out what the eigenvalues are. The eigenvalues are simply all the possible values of x along the real axis. We could erect one of these delta functions anywheres. Any place we erect it, it will be an eigenvalue, or sorry, an eigen, sometimes I use the word eigenfunction. Eigenfunction is another word for eigenvector. It's an eigenvector of the operator x with eigenvalue lambda, and lambda can be anything on the real axis. Okay? So that's our first example of a Hermitian operator, a spectrum of eigenvalues. Spectrum just means the collection of eigenvalues, orthogonality of the different eigenvectors. And now let's discuss what a wave function really means. Psi of x is called a wave function, but let's discuss the following. For simplicity, I'm going to take the height of this function to be 1 over the thickness of it, and that means the area under it is 1. The area under a delta function is 1. That's the definition of the delta function. Well, let's take psi of x and take its projection, its inner product, with the eigenvalue, with the eigenvector lambda. Eigenvector lambda corresponds to a particle located at position lambda. In other words, it's the eigenvector of the position, and it's the state in which the position has a definite value. All right. What is this inner product? This is the inner product gotten by taking psi of x and integrating it with the wave function corresponding to lambda. But what is the wave function corresponding to lambda? It's delta of x minus lambda dx. This is the inner product of psi with the eigenvalue lambda, with the eigenvector lambda. Psi of x integrated with the eigenvector. This function is equal to something special. It's equal to something very simple. Remember that psi of x is 0 everywhere except at x equals lambda. If it's 0 everywhere at x equals lambda, except x equals lambda, it's only sensitive to the value of psi at x equals lambda. In other words, over this whole tiny, tiny range here, the only values of psi which are important are the values of psi at x equals lambda. Since the height of the function, since the area under the function is 1, it's easy to prove. Okay, here's the argument. Between this point and this point, psi doesn't vary very much, assuming that psi is nice and continuous. And if we take this interval sufficiently small, psi will not vary very much across the delta function. All right? What is it right at the delta function? It's just equal to psi of lambda. So to a good approximation and a better and better approximation as I shrink this interval here, I can simply replace psi of x here by psi at that one point, psi of lambda, times delta of x minus lambda, integral. Psi of lambda now can be brought outside the integral. This doesn't depend on x anymore. So we bring it outside the integral, and we just have to integrate delta of x minus lambda. The integral of delta of x minus lambda is 1 because I've defined the area under the function to be 1. So we just read off from this then that this is just equal to psi of lambda. This is equal to psi of lambda. In other words, the wave function itself, psi of lambda, or we could call it psi of x, we could replace x by x here. We can read this as saying the inner product of psi with a state which is localized at position x is just the wave function psi of x. That's what psi of x is. It's just this inner product. With this inner product now where I've changed notation, instead of calling the eigenvalues lambda, I've called them x themselves now. This corresponds to a wave function localized right at x. Okay, so where are we now? We now know mathematically that psi of x is sort of just a component of the vector psi along the basis vectors x. But now let's use the postulate. What have we done? We've erased all the postulates. Oh my goodness. What was the fifth postulate? Not Euclid's fifth postulate, but the quantum fifth postulate. It was about probabilities. It said that the probability for getting a particular lambda is the square of the vector projected onto the eigenvector lambda. In this context, it says squared. In this context, it says the probability for detecting a particle at position x, the probability to detect a particle at position x is just equal to psi x quantity squared, or absolute value squared. But what is this psi x? It's just psi of x times psi star of x. In other words, we've now found out what the meaning of psi of x is, that it's the thing that you well, it's not the full meaning of it, but a partial meaning of it is it's the thing whose absolute value squared is the probability to detect a particle at x. So we've used the postulates of quantum mechanics to determine, in terms of the wave function, what the probability to locate a particle at x is. Yeah?
So we've gone from psi being any old function to psi being some specific function?
No, I mean, psi could be any old function, but for any old function, there will be a probability distribution. Whatever psi is, and psi can be complex. Psi need not be real. It can be negative in places. So psi is some complicated, complex function that can be negative, positive, and imaginary, and all those things. If you take it and multiply it by its complex conjugate, you'll get something real and positive. That real positive thing is the probability to find the particle at different locations on the x-axis. That's the implication of the postulates of quantum mechanics. In particular, it says that probabilities are given by the squares of certain complex functions. Now, if all you get out of it was the probability for finding particles in different places, you might say, why the hell don't I just define the probability as a function of x? Why do I go through this complicated operation of defining a complex function psi and then squaring it? The reason is because there are other things that you could measure besides the position of the particle. There are other Hermitian operators which correspond to other observables. In particular, let's think about other possible Hermitian operators. I'm just going to give you another simple one. The simple one corresponds to a very basic thing in quantum mechanics. I'll name it as we go along. But before I name it, let's just define it in an abstract operator sense. Not abstract, a concrete operator sense. Again, we're still doing the particle on the line. Its states are described by functions psi of x. In other words, the vector space is again the functions of x. Same exact setup as before. But now I'm going to think about a different observable which is characterized by a different operator. The operator now is not multiplication by x. Multiplication by x is what we did over here. Now a different operation. Differentiation. Just differentiate psi of x. That's an operation. In fact, it's a linear operator. If I differentiate, I can differentiate the sum of two functions. I can multiply the function by a number. If I multiply the function by a number, its derivative is just the numerical number times the derivative of the original function. I can add functions and differentiate them. D by dx is a linear operator acting on the space of function psi of x. So this is another operator. Does it correspond to an observable? Not quite. Not quite because it's not Hermitian. It's what's called anti-Hermitian. Anti-Hermitian means all you have to do is multiply it by I to get something Hermitian. But let's first prove that it's not Hermitian. In fact, I'll prove that it's anti-Hermitian. Let me tell you what anti-Hermitian means. I'll just define it right now. It's a class of operators that were discovered by Hermite's aunt. Anti-Hermitian, no, that's not true. All right, anti-Hermitian, remember what Hermitian means. Hermitian means that A psi B is equal to the complex conjugate of B, oh, what am I saying, psi, H, excuse me, H, A, complex conjugated. That's the meaning of Hermitian. In particular, it says that A.
You want to write that star there.
I don't? Why not? Don't I? I think I do. Yeah. All right. Anti-Hermitian says that AHB is equal to minus BHA. That's called anti-Hermitian. If you spend 5 minutes, you realize that for every, this is anti-Hermitian. Let's call it H, what about the hat?
Operator?
You mean this notation here? Yeah, we're splitting hairs, but properly so. I don't know where to do it. I don't know what to call it. Let's just call it anti-Hermitian.
We still need the star there, right? Conjugate.
Yeah, sorry, star. It's exactly the same as Hermitian but with an extra minus sign. It's very easy to prove that if you have an anti-Hermitian operator, if you multiply it by I, it becomes Hermitian. And the reason is because the complex conjugate of I is minus I.
Because it rotates the H on its side.
Okay. If you have an anti-Hermitian operator and you multiply it by plus or minus I, let's say minus I, oh boy, this looks like I, doesn't it? Okay. Anti-Hermitian. Anti-Hermitian. It's not A times H. It's anti-Hermitian. If I take an anti-Hermitian operator and multiply it by I get a Hermitian operator. That's a little theorem to prove. Do it yourselves. But it just follows from the fact that the complex conjugate of I is minus I. So, no H bar, please. Not now. You're confusing me. Okay. But in fact, d by dx is anti-Hermitian. But let's just see why it is that that d by dx is not Hermitian and why you discover an extra minus sign there. I'll tell you what, let me cut it short. Let me cut it short by simplifying. I'll tell you right now that the thing which is Hermitian is I times d by dx. In other words, or minus I, doesn't matter, I or minus I. Minus I d by dx on psi of x is or minus I d by dx is an operation. It's a linear operator on the space of functions, and it's a Hermitian linear operation. Let's see if we can prove that. Let's see if we can prove that it's Hermitian. And the simplest way to prove it is to prove that let's give it a name. I'm going to give it the name K hat. I'm not going to call it H. I'm going to call it K, but it's Hermitian. K hat on psi of x. The simplest way to prove it is to prove that for any psi k psi is real. Now that sounds a little odd because k has an I in it. It looks awfully much like it's going to be imaginary, but it's not. Let's check it. We have to calculate psi star. That's the left, that's the bra vector. K hat is minus I d by dx times psi, or just the psi dx. Now it doesn't look real, but it is real. To prove that it's real, we want to prove that it's its own complex conjugate. So let's prove that this thing is its own complex conjugate. And the way we prove it is by integrating by parts. Does everybody know how to integrate by parts? Integrate by parts is a very simple thing. If you have the product of two functions, f of g, f times dg by dx, and you integrate the product of a function with the derivative of another function, the answer is minus g times the derivative of f. You simply interchange which of them is differentiated. Instead of differentiating g, we differentiate f, and you throw in an extra minus sign. That's called integrating by parts. It's a standard elementary calculus theorem. What am I missing out of this? The endpoints of the integration, but the argument for the endpoints is that I've chosen functions psi which go to 0 far away. If they go to 0 far away, I don't have to worry about the endpoints of the integration. So let's integrate this by parts. To integrate it by parts, I simply throw in another minus sign. This must be equal to, plus, we have to change the sign, plus I, times the integral. And now I interchange which of the things gets the complex or gets the derivative. It becomes d psi star by dx times psi. That's this. All right, so I have this is equal to this. Integral psi star times minus I d psi by dx is plus I times integral d psi star by dx. Now, I assert that this, the second term, the second expression, the right-hand side, is simply the complex conjugate of the top. Let's check that. Let's take the complex conjugate of the right-hand side of the equation. The complex conjugate of the right-hand side, first of all, has the complex conjugate of I. So I'm going to rewrite the complex, I'm going to write the complex conjugate of this. I'm not going to write equals, just complex conjugate. Here it is, CC, complex conjugate. What's the complex conjugate of I? Minus I. What's the complex conjugate of psi? Psi star, right? What's the complex conjugate of d psi star by dx? D psi dx. But look, the complex conjugate of the right-hand side is just the left-hand side. Minus I psi star d psi by dx. So what have I proved? I've proved that this is its own complex conjugate. By integration by parts, I prove that the left side of the equation is equal to the right side. But then I prove that the right side here is just the complex conjugate of the left side. No. Yeah. So I prove that this is its own complex conjugate. If it's its own complex conjugate, it means that it's real, and it means that minus I d by dx is a Hermitian operator. Right. The extra sign, or this, it's a little surprising. You might have thought that just d by dx was Hermitian, but it's not. Okay. So minus I k, which is just minus I d by dx, is a Hermitian operator. Let's find out what its eigenvectors are. If it's a Hermitian operator, it must have a lot of eigenvectors. Let's see if we can find out what the eigenvectors are, and then see if we can interpret them and figure out what observable, what quantity that you can measure this operator k corresponds to. Okay. So, here's the eigenvalue equation. Let's write the eigenvalue equation. Minus I d psi by dx should equal, this is the action of k on psi. This is k on psi. K is minus I d by dx. If psi is to be an eigenvector, what does the right side have to be? Lambda times psi, where lambda is the eigenvalue. Let's call the eigenvalue k. Just to call it by its traditional name, let's call it little k. This corresponds to an eigenvalue times psi of x. So we're looking for functions. The eigenvector functions are those whose derivatives, or minus I derivatives, are equal to k times psi of x itself. Everybody know how to solve an equation like this? Anybody know how to solve an equation like this? Exponentials. Exponentials. The solution of this equation is that psi of x is proportional to e to the I kx. Okay? Let's check that. Rather than solve it, let's just check that this is the solution of the equations. E to the I kx, of course, means cosine kx plus I sine kx. Let's check that. Let's check that minus I d psi by dx is k times psi. So to differentiate this, every time you differentiate it, it pulls down the coefficient ik. So d psi by dx is equal to ik times e to the ikx, which is just ik times psi. Now I want minus I times this, so let's multiply by minus I. What's minus I times plus I? Just 1. So we find out that this function here is an eigenvector of the operator minus I d by dx. Okay? So, in fact, we have found the eigenvectors of the operator minus I d by dx, and they are simply the functions cosine x plus I sine x. Let's think about those functions for a minute. Those functions are very, very different than the eigenvectors of x. The eigenvectors of x were these highly peaked delta functions. These functions here are spread all over the map meaning x. They're spread all over the map. They're oscillations which endlessly go on and on. Cosine looks like this. Sine looks like, well, let me draw sine in blue.
Oh, but it's I sine x, though.
Yeah, I can't draw I sine, no. But I can draw sine. I'm not saying, don't add the blue to the black. Multiply the blue by I before you add it to the black. But I can't draw that. Let's see. It starts here and it has the same wavelength, I don't know, it has the same wavelength, but it's 90 degrees out of phase. We know what sine and cosine look like. I'm not going to try to draw them. All right. This is the eigenfunctions, and it's got a plus I cosine kx plus I sine kx. All right. What is the magnitude? Supposing I multiply psi of x by its own complex conjugate. What do I get? 1, the number 1. Psi times psi star is just 1. E to the ikx times e to the minus ikx. E to the minus ikx is the complex conjugate of psi. Psi times psi star is 1. Remember,
That's not a constant anyway.
yes, there's an ambiguous constant in here. All right. But whatever that constant is, psi star psi is constant. That means that the probability to find the particle anywhere in space is uniform. Complete uniform probability distribution. There's no information in this where the particle is, but the function oscillates, and those oscillations must mean something. Okay? Let's see if we can figure out what they mean by using, first of all, let me say this, first of all. According to the postulates, k corresponds to some kind of observable. Its eigenvalues are little k here, just numbers. Any number from minus infinity to plus infinity will do, will be an eigenvector, will be an eigenvalue. What are we to call this operator? Well, we've got to give it a name. To give it a name, I'm going to relate this to some very primitive observations about quantum theory before real quantum mechanics was discovered. Going back to Einstein and de Broglie, this is for the purpose of giving it a name. Yeah.
In the derivation so far, you assume that psi raised to 0 at infinity.
Yes, you're entirely right. And in fact, there are no true eigenvectors of psi of x which go to 0 at infinity. But you can find functions which are arbitrarily close to this, arbitrarily close to solving this, by taking functions which oscillate and then far away, gradually diminishing in magnitude. You are right. I don't want to get into that now, the normalization of the functions, but you are right. And one has to do a little bit of explanation here about why I'm allowed to get away with functions which don't go to 0 at infinity. I didn't want to do that now. Mostly I wanted to illustrate the principles by working out some examples of eigenvectors, eigenvalues, and so forth. So allow me the freedom to ignore that issue of whether the functions go to 0 for the moment. At least they don't blow up. At least they don't get big. And that is important. For the moment, I want to find out, I want to name this observable If I name it, I mean I want some intuitive connection with something that I already know. All right, so the eigenfunctions after all are the wave functions which correspond to a definite value of this observable. What shall I call that observable? Well, first of all, let's think about the wavelength of these oscillations. These are waves. Right? The wavelength is this distance. The wavelength is the distance that you have to move before cosine kx comes back to itself. Cosine 0 starts at 1. How far do you have to move before cosine comes back to 1? Well, the answer is 2 pi, but it's not x equals 2 pi, it's kx equals 2 pi. Right? So the wavelength corresponds to k times the wavelength L is equal to 2 pi, or the wavelength here, L, is equal to 2 pi divided by k. So we could either characterize these waves as having a certain value of k, a certain eigenvalue, or we could equivalently characterize them by their wavelength, and their wavelength is L. Right? Now, next, we make use of an intuition which goes back to de Broglie and also to Einstein, that if we have particles corresponding to waves of a given wavelength, those particles have a certain momentum. Now, we're only using this to name a certain thing. I cannot legitimately claim at this point to explain to you why we're going to call something momentum. We will do that later. In order to see that something is really behaving like momentum, we have to do a lot more. But for the moment, I just want to put, sort of a, what shall we call it? Just throwing a bunch of stuff together that we've seen earlier in order to give this thing a name, a familiar name. All right, what de Broglie said is that if we have a beam of particles corresponding to a wave of wavelength L, that those particles have a momentum. And the momentum, let's call the momentum P. It's the same term that we used in classical physics. Anybody remember what de Broglie said? P is equal to h over L. This is also the thing that Heisenberg used. The shorter the wavelength, the higher the momentum of the corresponding particles. And it's Planck's constant h, which goes in there. So if you have a set of photons, for example, a set of photons which are described by a classical wave of wavelength L, then what Einstein knew, and which he didn't say, but what de Broglie reinterpreted and generalized to any old particles, not just photons, is that the momentum of those particles described by a given wave is given by h divided by L. Well, L is 2 pi over k, so let's plug that in. That says that this is h, and then we have to turn L over, so that's k divided by 2 pi. H over 2 pi has another name. It's called h bar. So this is h bar, Planck's other constant, times k. Momentum is h bar times k. So we now have an interpretation. It's an interpretation that we're going to have to check later when we understand the connection between quantum mechanics and classical mechanics. Momentum is a classical concept. We're now using sort of seat-of-the-pants, old-style quantum mechanics, the intuitive, confused ideas of, that were before Heisenberg and Schrodinger, but let's use them and justify them later. That wavelength and momentum are connected in a certain way. Where is it? Wavelength and momentum are connected in a certain way. And if I then plug in, I find that momentum is connected to k. Momentum is h bar times k. Do I have that right? Yes. Yes. Momentum is h bar times k. Okay. Well, that now interprets for us what the physical meaning of the observable k is. It's just the momentum of a particle, except in units of h bar. K is just the momentum of a particle in units of h bar. If you don't like calling it momentum, don't call it momentum. Just call it the observable k. All right? You can just call it the observable k, and you see that its eigenvalues and its eigenfunctions are just the numbers k and the wave functions e to the ikx. The interesting point here is that whatever k is, it is of course the momentum, but whatever k is, the eigenvectors of it are completely different than the eigenvectors of the position x. The eigenvectors of the position x are these high, narrow functions, which are also slightly ill-defined, and the eigenfunctions of momentum are these functions which oscillate on and on forever and ever and have a completely uniform probability distribution. In each case, there's something mathematically a little wrong. In one case, this is clearly a thing which needs a better mathematical definition, and in the other case, we are allowing functions now which don't go to 0 and infinity. These two things are related, but without being too precise and without being too mathematically rigorous, we now see that whatever these objects are, whatever these wave functions are, they're completely different for position and momentum. In particular, no eigenfunction of position is also an eigenfunction of momentum. Well, that sounds familiar. It sounds something like the uncertainty principle. If the eigenfunctions of position are the states in which, if you measured the position, you would know exactly what it was, and if the eigenfunctions of momentum are the wave functions which correspond to a definite value of momentum, it's quite clear that they sort of clash with each other. If you know the position of a particle, that's equivalent to saying that you know that its wave function is peaked like that. If you know the momentum of a particle, it means that the wave function is spread out all over the place. It can't be both. And that, of course, is the source of the uncertainty principle, which we're not going to do tonight, but it's the source of it. And it's an example of incompatible quantities, quantities which correspond. Another way to say it is if you think of the eigenfunctions of position as forming a basis of vectors in a very high dimensional vector space, but I'm going to draw it as just three-dimensional, then the eigenfunctions of momentum are simply different eigenvectors pointing in different directions so that no eigenfunction of position is also an eigenfunction of momentum, and no eigenfunction of momentum is an eigenfunction of position. They correspond to different basis sets which are at angles relative to each other. We've now kind of gone through one example of a space, of a vector space, the space of functions of x, and the interpretation of a couple of different linear operators. The linear operator corresponding to position and the linear operator corresponding to momentum. What would we really have to do to see that it's more or less clear intuitively that a wave function which is peaked at a location in space corresponds to a particle at that location of space? What would we really want to do in order to see that, that this other observable really does correspond to the momentum of a particle? Well, momentum is a classical concept. And in order to understand in what sense this thing corresponds to momentum, we have to be able to understand the limit of quantum mechanics in which it behaves like classical mechanics. It's quite obvious that there must be such a limit. If quantum mechanics governs everything, it governs electrons, it also governs bowling balls. Right? But bowling balls are very heavy, and they correspond to a limit of quantum mechanics, a limit of quantum mechanics of heavy objects. What we would have to do in order to see that this object that I've called momentum really behaves like classical momentum is to understand that limit better. And we will. We'll come back to that limit. For the moment, calling k momentum or calling h bar times k momentum is just a name. It's just a name for an object, a name for an observable. Okay, any questions? Yes?
I have a comment.
Yeah.
The psi of x equals e to the I kx can be thought of as a function twisting around the x-axis. I
Good.
think that helps visualize it.
I agree. So let me say, good. So let me just restate what you just said more completely. The complex number e to the I kx is a number whose magnitude is 1. E to the I kx times e to the minus I kx is 1, which means that it's a number in the complex plane which lies on the unit circle. Okay? And of course, it's equal to cosine of something, cosine kx plus I sine kx. Now, if I imagine the complex plane being oriented this way, and the x-axis, oh, this is different x, sorry, this is psi. Psi is a point on the complex plane, and if it's of the form e to the I kx, that means it's on the unit circle here. Psi is on the unit circle. This would be the real part of psi in this direction, and the imaginary part of psi in that direction. Let's not confuse x and y with the position of the particle. Now, supposing I draw the complex plane this way. Remember, the wave function is a complex function, and the x-axis, the position of the particle that way, that means that at every point of space, I could draw the complex plane and plot psi as a point on the complex plane at every x. Okay. So at every x, psi is a point on the complex plane, and in fact, for this kind of function, it's a point on the unit circle. Right. So as was pointed out, what it corresponds to is a point which, as you move along, winds around like a helix, winds around on the unit circle like a helix. That may help some people. It helps me. Small k means very long wavelength, means it winds slowly. Small k means large wavelength. Right. Large k is small wavelength. So large k means that it varies very quickly. Right. So large k means it winds very quickly as we move along. Small k means that it winds very slowly as we move along. Right. Yeah, that's a good point. Any other questions or comments? Some of the comments are helpful, so.
On your postulates, you didn't say anything about like quantum collapse.
No, not at this point, not yet. Not yet. One of the point that we haven't talked about, which we'll talk about next time, we have not talked about the probability for different momentums. We talked about the probability for different positions. It was just psi star of x, psi of x. We have not talked about the probability for different momenta. All right, so we'll talk about that next time a little bit. And right, we have not talked about, basically we have not talked about the measurement process itself and what it does to the system, the actual act of measurement. We only said the probability for a given measurement is given by this or that. Yeah.
K and L are inversely proportional, so big K is small.
Big K is small l and big L and vice versa. That's what we just said.
Well, we said the opposite.
No, we didn't. We said small k corresponds to slow variation, which means big L. Large k corresponds to rapid oscillation, which means small l. Yeah.
Intuitively, it would seem that momentum is a differentiator to the effective time, not the effective position.
Right.
The differentiator is
Well, okay. Momentum we usually think of as having to do with dx by dt. Right. What we do, all right, so let me state it for you then. There's an approximation to quantum mechanics which is good for heavy particles and heavy objects, and in that approximation, the wave function moves around, tends to form a lump, and this lump moves around. What we're going to want to prove is that this lump moves around in more or less in accord with the classical equations of motion. And we're going to want to prove that the velocity that it moves around with is related to how fast the wave function is varying. So if we have a wave function which varies quickly like that, so that it corresponds to a large k, we're going to want to discover that it moves across the blackboard faster as if it was a high momentum particle. But to do that, we have to understand how things change with time. We haven't even brought time into it yet. So the correspondence between momentum and what we normally call classical momentum is through the question of how wave packets move around. And we're going to want to see that wave packets move around in accord with pretty much the classical equations of motion. Good. Any other questions? Got one more minute before I collapse, before my wave function collapses. You know how many hours I've been teaching today? 4. My father used to work 18 hours a day, but you know. You're supposed to feel sorry for me now.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.